share the screen now. All right, now we're gonna be talking about an apparatus to, well, find out what pressure the air is at. So this thing is called a barometer. I don't know if you guys have heard of this. I think some of you should have. So, barometer. If you look at I don't know if you guys look at the weather, but the weather app on your phone, if you look at it, it says, well, how many, I don't know what units they use, I forgot. Probably use bars or something. But yeah, that's the air pressure, the air pressure. Do you guys remember in I think it's 5th grade we learn about weather, all right? You guys remember how the air pressure has to do with rain, all right? So how do they measure air pressure? They actually use this thing. Yeah, I think a lot of people actually still use this because it's actually not bad. It's a pretty accurate piece of equipment. So, so you use to measure the air pressure. And how this thing works is basically, well, you have mercury, all right? Mercury, and basically this tube is filled with mercury, all right? It's filled to the very top, all right, with mercury. And then you would, dip the open end into a bowl of mercury. And then, so what that does is basically it forms this vacuum, all right, in the tube. There will be a vacuum at the top. And so you want a vacuum because because air has pressure, right? As we said, all air has pressure. If you have air in here, they'll be pushing against the air outside and you wouldn't get an accurate reading. So actually you want to fill this tube with mercury and you want to flip it very fast, all right? You want to flip it into a bowl of mercury. And then when it drops, it will form a vacuum here. So, and then that will give you a pretty accurate reading of the atmospheric pressure. And basically how you read it is how tall this tube is. And as you can see, normally at the sea level or 1 atm of pressure, right? So at sea level, you have about 760 millimeters, all right, or 76 centimeters. So that's what we call, mmHg, millimeters of mercury, all right? Hg is mercury, all right? So that's why, at the sea level, we would say it's 760 mmHg. All right, and also this unit can be also called torr, T-O-R, torr, right? That's why some people also say it's 760 torr for 1 atm, right? That's what it is. And also, actually, notice that 76 centimeters is not exactly short, all right? I don't think you want to be putting that on your table. Probably don't want to spill mercury all over yourself, right? So yeah, this apparatus is not exactly a small one. We have improved ones now that you don't have to use mercury for this. There's some other designs, especially for, airplanes and stuff. You don't want to be carrying a long tube of mercury, right? So actually, a lot of places now to have something that looks like a clock, I don't know how that works, but yeah, have much better designs now, I guess. But that's the OG, all right? So that's the barometer. Now I'm gonna be talking about the manometer, because all gases have pressure, not just the air around us. Now, sometimes we might want to know how much pressure a gas has, and how do we do that? Well, we use something called a manometer. All right. So you might notice it's pretty similar. but there's a couple key differences. First of all, well, there's two kinds. If you notice here, there's two kinds. There's two kinds. So why would that be? Well, this kind is pretty similar. There's a vacuum on top. You can see here it's sealed. There's a vacuum in here, and that's great. All right, that's great because the difference in height is just a pressure for gas. Right? No mass required. Literally just take a ruler, the height is just how much pressure you have. All right, because remember, millimeters of mercury is an actual unit. All right, it's an accurate one and it's an actual unit. So yeah, let's take this. But there's another one. Sometimes this is called an open tube or open end manometer. All right. So for this one, then the air pressure outside, all right, in our atmosphere will be actually pushing against your gas in here. So that's why this one is usually used for gases that have pressures higher than the atmospheric pressure, right? And this one is used for gases that have lower pressures than the atmospheric pressure. And why might you want to do this? Because if you put a gas with a lot of pressure, all right, in the close end, well, either you're gonna have to make your tube very, very long, or it's just gonna be, shot all the way up to the top, and then it wouldn't give you an accurate reading. All right, you'd be past the limit. And also for this one, you wouldn't want a gas with too low pressure because then the air pressure would actually push the mercury to the other side. All right, and then you'll be having to use that atmospheric pressure to minus the height difference. All right, so that's why usually open end you measure gases with higher pressure, close end you measure gases with lower pressure. It just makes more sense to do it that way. All right, so close tube manometer, all right, as I said, is used to measure pressures below atmospheric pressure, where the open end is suited for measuring pressures equal to or greater than. All right. And also, nearly all barometers and manometers use mercury as a working fluid, despite the fact that it has, a very harmful vapor, and also it's pretty toxic. I mean, it's really toxic. Also, to add on to that, it's a liquid at room temperature, and it likes to vaporize. So guess what? If you have mercury, you're gonna be smelling it. You're gonna be, inhaling the liquid, not the liquid, inhaling the mercury gas into your lungs, which kills you very fast. So why do we use mercury? Do you guys have an idea of why we might want to use mercury, even though it can very easily kill us? Low density. Well, actually, let's let somebody else answer it. So let's see. Somebody else. Nuclear weapon. Yes. Yes, I love using mercury for nuclear weapons. All right, if nobody else is gonna answer, then let's just move on. So yes, it's high density. Also, I don't know why you guys all use direct message. That's fine. Whatever. Oh, oops. All right, so yes, it's high density. So the reason is that mercury's density is 13.6 grams per milliliter. So 13.6 grams per milliliter is actually pretty high. Yes, it's higher than most other fluids or liquids. Yes. So if you've seen, you probably search this on like YouTube, all right? A lot of stuff floats in mercury. If you look like iron, right? Anvils. You can throw an anvil into a pool of mercury and it'll float. I think there's a couple of videos on YouTube showing that, all right? So it's very dense liquid. It's a very, very dense liquid, denser than a lot of solids even. All right. So because the height, all right, the height of the liquid in the column, it's inversely proportional to your density, which means that the more dense it is, the less height you need. So mercury, as we said, at the ground level or at sea level, all right, it's about 760 mm, so 76 centimeters. That's, not even a meter, all right? To account for higher, lower pressures, you might want a tube that's a meter tall. But what if I use water? What if I use a tube of water to measure it? Then my tube of water will be 10.3 meters tall at sea level, all right? 10.3 meters. That's like 5 grown men stacked on top of each other. Actually, probably close to 6, all right? Probably close to like 6 grown men stacked on top of each other, all right? I don't think you're going to be carrying that anywhere. So yeah, that's why you want to use mercury. Yeah, unfortunately, you will have to use mercury if you don't want 10.3 meters. And also that creates a problem, all right? 10.3 meters. If you're gonna be building it even higher, because to account for higher, lower pressures, you're gonna be building it to be even taller, all right? It's gonna change a lot based on the pressure. Probably want at least 11 meters. And then first of all, how do you even get all that? How do you even build that? And how do you pump the water in there to form a vacuum? And also, if you have a vacuum over like a meter of empty tube, is your tube gonna shatter? So that's why it's really impractical for a lot of liquids to act in a barometer. All right, so now we're gonna be talking about some gas laws. Well, yeah, have fun. I don't know why our teachers want us to know, who came up with what law. Honestly, I don't think it's that important, but probably occurs on a test, so you might want to memorize these. All right. So the first one is Boyle's law. Now, Boyle's law is basically saying that the pressure of and fixed amount of gas. All right. So basically, don't change how much gas you have. If you started with one, I guess, can of gas, you're gonna be ending up with a can of gas. All right. So when you're not changing the amount of gas you have at a constant pressure, it is proportional to the volume of the gas. So okay, the pressure, all right, of a fixed amount of gas. So you're not changing the amount of gas and you're not changing the temperature. So you have two constants. But a lot of these laws, it's when you have two constants held constant, all right? So when your pressure, or not when your pressure, when your amount and your temperature is held constant, then the pressure and the volume are inversely proportional. And yeah, hopefully that makes more sense. And also, we would write this as, let me get my here. All right, we will write this as that P. This means it is proportional, all right, the fish to 1 over V. All right. So it's inversely proportional to the volume. All right. P, fish looking sign, 1 over V. All right. So that's basically what Boyle's law is. Pressure and volume are inversely proportional. But also remember to keep the two other constants, well, constant. Keep the two other variables constant. Right. All right, so the graphs demonstrating this law would be, well, first of all, you need the pressure and the volume. And notice here, pressure and volume are inversely proportional. All right, this is, you see this graph? All right, the higher volume you have, the lower pressure. All right, the higher pressure, the lower volume. So it's an inversely proportional graph. All right, this also shows this. Why? Because as we said, inversely proportional is basically proportional to 1 over V. So see, P and 1 over V, now it's directly proportional. This is called linearizing your data, all right? So making your data in the form of a line. All right, so yeah, pressure and 1 over volume. All right, and also because of this, we come up with the equation that P1 V1 equals P2 V2, all right? Because it's, well, you can see here, I think like the graph would demonstrate this best. You see the pressure and the volume here, if you multiply that, would equal to the pressure and the volume here, right? 0.6 times 2 and 0.3 times 4. That's the same thing. So P1 V1 is equal to P2 V2. All right. Now, moving on. Oh, moving on. All right, Charles law. So, also Charles law, there's another name for it. I think it is the Charles and Gay-Lussac's law. Yes. Funny name, but yeah, it's not so funny when you see his name on your test. So yes, I think I'll usually just say Charles law, but in your book, they said that it can be called both Charles law or Charles and Gay-Lussac's law. Yeah, so basically it states that the volume of a fixed amount of gas is, or maintained at constant pressure, is directly proportional to the absolute temperature of the gas. So volume is directly proportional to the absolute temperature. That's basically what it's talking about. So what's an absolute temperature? Well, it's something that you might have heard of. It's called kelvins, right? Make sure when you're dealing with gases, you're always dealing with kelvins, all right? I know it's a weird unit, all right? It's a weird unit, but when you're dealing with gases, we don't want to use a relative unit like Celsius or even worse, Fahrenheit, disgusting, Fahrenheit, it's good enough. You want to talk about how hot the day is. You don't want to be talking about how much pressure gas you have, all right? So yeah, make sure to be using kelvins. So here's two equations that you should know from this law. So V1 over T1 is V2 over T2. P1 over T1 is equal to P2 over T2. Should make sense. So the last one, Avogadro's law. Avogadro's law states that at constant pressure and temperature, the volume of a gas is directly proportional to the number of moles of gas present. Now that's basically saying that if at this constant or if at this pressure and temperature, all right, 20 liters is 1 mole of gas, then any gas, all right, it doesn't matter if it's oxygen, doesn't matter if it's carbon dioxide, doesn't matter what it is. If I have 20 liters of another gas, all right, it's still gonna be 1 mole of that gas. So if I have 40 liters container, I know in there there's 2 moles of gas, all right? So yeah, that actually makes some calculations a little bit easier. And actually at what we would call standard temperature pressure, well, we'll talk about that later, STP. All right, now let's talk about the king of all equations in honors chem, all right? The single king of all equations that you will learn in honors chem, probably because it's the only equation you kind of have to remember. All the others are gonna be given to you. But this one, first of all, you have to memorize it. Second of all, you're gonna be using it a lot. Actually, kind of useful. PV equals nRT. All right, PV, you should know what it means: pressure and volume. T, temperature. That'll make sense. Now, what's N and R? N is the number of moles. All right, number of moles you have. And then what's R? R is the proportionality constant. It's basically just a constant. All right. You're probably gonna be dealing with ATMs. You know, as I said, nobody uses Pascals. You know, you're probably gonna be dealing with ATMs. Maybe you'll deal with Tor. Anyways, for ATMs, usually it's just ATMs. You just have to remember that R is 0.0821. No, but we'll talk about that later. So an ideal gas, first of all, this law is called the ideal gas law. So we're going to be dealing, or we're not going to be dealing with ideal gases, but we can assume that the gases you deal in honors chem are all ideal gases. Which, I mean, usually it's not that far off. I mean, you're going to be dealing with like hydrogen and stuff, you know, when it's small enough, you can assume it's an ideal gas. But anyways, you know, basically a hypothetical gas that where the pressure, volume, temperature, behavior can be completely accounted by this equation. We'll learn next week and modify the equation for gases that's not so ideal. Which, you know, I don't know how old you guys are, like 14, 15. I mean, hopefully you've seen that the world's not ideal. So yeah, don't be surprised when you have to learn another equation for not ideal gases. But you know, I think honors chem don't really use that much. I mean, AP chem doesn't use that much either. Just use a little bit of that equation because it is. I mean, both of these equations basically plugging numbers in the ideal gas equation or the other one. So yeah, it shouldn't be that hard. All right, so usually for these kind of calculations, we're going to be doing it, unless specified, you're going to be assuming it's STP, all right? So standard temperature pressure. Basically, it's 0 degrees Celsius and 1 atm. But remember, we're going to be using kelvins. We use kelvins, not Celsius. 0 Celsius doesn't mean anything. It's 273 kelvins, all right? So when you say STP, that's 273 kelvins and 1 atmospheric pressure, or 1 atm of pressure, right? Or 760 torrs, remember. All right, so, here you go. Oh, by the way, I was supposed to be talking about something else. Why don't we use Pascals in chemistry? Because 1 atm Guess how much that's equal to in pascals? It's equal to over 100,000 pascals. So yeah, don't use pascals. We don't need it. All right, so sulfur hexafluoride, SF6. So colorless, odorless, very unreactive gas. Yes, it's actually what you feel tennis balls with. I don't know why. Calculate the pressure exerted by 1.82 moles of the gas. In a steel vessel of volume 5.43 liters at 69.5 degrees Celsius. And as I said, remember, don't use Celsius, use Kelvins. How do you convert from Celsius to Kelvins? Hopefully you know. And also, R is 0.0821. I told you that. All right, you guys can give me your answers, or if you don't know how to find the answer, then well, you can give me your best guess. Remember, PV equals nRT. Literally, this entire, not even this entire chapter. I think this entire year, that's like the only equation that's really meaningful to you guys. So, PV equals nRT. If you don't remember anything from this year, you probably remember this equation. I need to make it bigger, geez. All right, chat. All right, negative 5.6 ATM. All right, good guess. All right, apparently we're gonna be running out of time in 10 minutes again. Jeez. Zoom really likes getting its money, huh? 9.42. All right. I don't know if that's the right answer. Actually, I have to check. Let's see. Let me check real quick. Oh shit. I know what. I'll just use my I'll use my other computer here to check. All right. A couple people are saying 9.42. I think that should be the right answer. All right, so next question. Let's see, where did I find this question? I think that's all right, yes, 9.42. If you guys got 9.42, then that is the correct answer. Do you guys need help on this? Hopefully not. If you guys need help, then I guess you can do your raise your hand or something. I don't know. I'll be checking if anyone of you raises your hand. Or just type in chat to something. If you don't need help, then we'll be moving on. But yeah, it's just using the equation. All right, just manipulating this equation. All right, I don't see anyone needing help. I guess we can move on. Yeah, just plug in the numbers. All right, just plug in the numbers. But remember to change this to kelvins. All right. I think that's probably how people mess up the most. Change this to kelvins. How do you change it to kelvins? Add 273. All right, just add 273 to this. All right, let's clear my drawings. All right, moving on. All right, oh shoot, did I not copy the entire question? What happened? Oh, actually, that's fine. Yes, let's do this then. Calculate the volume in liters of 88.4 grams of CO2 at STP. Shouldn't be that hard. Remember, I have to change grams to moles, and then from moles, I have to change it to liters. And remember, they didn't give you a temperature or anything, but remember what STP means. Standard temperature pressure, all right? Remember that. Keep in mind, standard temperature pressure. Also, I guess I'll give you guys the numbers again. If you don't remember, let's annotate. So remember that R, go, geez, that's a bad equal sign. R is equal to 0, Pt.2, and also STP, remember STP, yes. All right. By the way, if you guys are having trouble calculating CO2's molar mass, CO2's molar mass would be equal to 44.01 grams for every mole, right? .044. Let me calculate this real quickly. Okay, I guess I'll just do this question, and then we might have to come back into the Zoom again because Zoom only lets us to do 40 minutes at one time. I don't know why. They're cheap. All right. Let me just do this question then. So you see 88.4 grams, all right? 88.4 grams. Every 44 gram is 1 mole, all right? I'll just divide that. and divided by 44.01 grams per mole. That gives me like 2 moles. All right. 2 point, how many moles? Let me see. 2.008 moles, whatever. 2.01 moles. All right. If I have 2.01 moles, remember I told you guys about Avogadro's law, right? Okay, let's look at this. Avogadro's law. All right. At constant pressure and temperature, the volume of a gas is directly proportional to the number of moles of the gas present. And it just so happens that I know how many liters is every mole of gas at STP. Every 22.4 liters is equal to 1 mole of a gas, any gas at STP. At STP, remember, at STP. So all I have to do is times 22.4. That gives me 44.99 liters. All right. And we have less than 1 minute before we have to move or rejoin the Zoom again. I don't know why. Like Zoom can't even give me like 1 hour. It's every 40 minutes. Every 40 minutes, they 1 hour. All right. Oh, how do I clear this? Oh, okay, that's fine. All right, argon is an inert gas. Well, let's have to join back in. So, yeah, whatever. You guys can start working on this if you want, or wait until we come back.